Our final postulate we'll talk about, postulate number 5, is one that we won't use very much in this class, basically hardly at all. But we introduce it here to introduce the idea of how do these wave functions evolve in time. So postulate number 5 has to do with that. So the wave function psi evolves in time according to the time-dependent Schrodinger equation. So this is similar to how when we were looking at the vibrating string, we could find how does the string vibrate over time. This is a similar idea. According to the time-dependent. We will almost always ignore the time dependence and look at the time-independent Schrodinger equation, but the time-dependent Schrodinger equation. And so this Schrodinger equation is that h is a function, h times, h operating, I should say, on the wave function, which can be a function of some positions and time. So we're going to look at this in one dimension, is equal to I h bar times the derivative of the wave function with respect to time. Okay, so the Hamiltonian usually doesn't depend on time. So the energy of the system usually is, the potential energy of the system usually is fixed, right? It's something that doesn't change over time. It changes over space, but not usually time. It can change over time. Then you have even more fun with this. But all the problems we'll consider in this class, we're going to consider Hamiltonians that do not change over time. They don't depend on time. And so we'll show that we can kind of ignore the time dependence for the most part. So we can use our separation of variables idea and say, well, let's take our wave function x as a function of x and t, and there's going to be a part that depends on time and a part that doesn't. So we'll have the wave function that depends on just the position, and then we'll have another part of the wave function that depends on time. We'll call it f as a function of t. So this is, yet again, our separation of variables. So handy, so useful. Okay, and this works as long as the Hamiltonian doesn't depend on time. And so we can then say that our Schrodinger equation is, we can separate out the time and position parts. So we'll put all the position parts on the left-hand side of the equation. So 1 over psi that just depends on x, h psi of x, and then put all the time stuff on the right-hand side. I h bar f of t, df of t, dt. Okay, and similar to before, these have to equal a constant, which is the energy. So we get over here we'll get h psi equals e psi. So this is the time-independent Schrodinger equation, what we'll always use. And then the time dependence, we get df dt, df of t, which is equal to negative I over h bar e f of t. So this is also, right, this is another differential equation. And in this one, we can simply integrate to find f of t. And we get that f of t is equal to e to the minus I e t over h bar. Okay, and so we can rewrite this. Let me just give myself some space to write here. So we'll have our time-dependent part. So we can say that x psi as a function of x and t is equal to psi of x. We can call this the stationary part of the wave function. Right, so this part doesn't depend on time, so that's why we call it stationary. It's kind of fixed in time. Times e to the negative I omega t, where we've defined omega to be equal to h bar, sorry, let me back up one more step. We'll let e equals h nu, h times frequency, or h bar omega, and so we can just make that substitution here. Okay, so all the time dependence is in this part of the function right here. Now, the reason we can ignore this is if we're just interested in probability distributions. So if we take psi star x of t, psi x of t, right, let's look at this probability distribution. So we'll have our, for just any generic wave function, we'll have a e to the positive I omega t here. So plugging in, this equation here. But because of the complex conjugate, we switch the sign on I. And then we'll have the same psi of x, and this still complex conjugate over here, e to the negative I omega t. And when we multiply all this together, we get psi star x psi of x, right? And so what we'll get is that this is our probability distribution doesn't depend on time. Under these assumptions that we have, right? And so the sorts of functions we'll find with the time-independent Schrodinger equation will give us what we call the stationary parts, right? These stationary states, and these are what are going to be sort of stable over time, and so these are what we think of as like energy levels, right? These are what we're going to get, and so we can ignore the time part for the most part in the sort of problems we're going to be looking at. For certain types of systems that you're looking at where you want to know how things change over time, obviously you care about this and you specifically include it. But for us right now, in a lot of the chemistry questions we're looking at, we don't really care about the time dependence, and the solutions we'll get won't depend on time, and so we'll call that good enough. So this is the only time we're going to talk about the time-dependent Schrodinger equation, and you can kind of forget about this for the rest of the class and just think about the parts that depend on the position of our particles.